So I'd like to give a talk about model evaluation with the point of view of machine learning, not the point of view of image processing, though they're related. So the first point I want to make, and I'm quite convinced about this, is that model evaluation is really the weak point, the bottleneck in machine learning. I don't know about image processing, it may very well be. Across the last, 15 years, something like this, machine learning has become an empirical science. We like it or we may not like it, this is the way it works. Sometimes we're not doing our empirical work solidly enough. So, a few examples. This is actually from images, so brain images here. Not classic images. A few years ago, back when I was still doing brain imaging, we ran a challenge where we wanted to. The goal of the challenge for me was to get an evaluation which was not biased by my own biases of the state of the art of what I was working on. And so we worked with clinicians, researchers in autism spectrum disorder, and we gave a simple goal. Given a bunch of images, approximately 2,000 brain scans, can you predict autism diagnostic status or not? And we gave incentives, 10,000 euros distributed amongst the leaders, and so we ran the competition. At the end, what we got was a marked difference between the public set, so this is a Gaël-like competition, so we're giving data to people, and on the public set they have the labels. On the private set they don't have the labels. And so what you're seeing is that there are a bunch of points that are severely optimistic. So people have massively overfitted the public set. They're predicting really well in the public set, but it doesn't carry over to the private set. And the important thing here is that the incentives were aligned. They had no incentives to do this. They just fooled themselves. We debriefed with some of the participants of the challenges, and clearly there was no clear understanding of what had gone on here. What has gone on is that they basically tweaked their algorithms, looking at their figure of merit, which is how well they predicted on what they had, and they used cross-validation. They didn't do things massively poorly, and as they tweaked, the number would go up, cool. They ended up overfitting. At the end of the day, this competition, the final result of this competition is that the best performers were fairly simple models. And models that seem really cool in publications, you graph neural networks, actually perform really poorly. One example. More recently, we looked at Kaggle competitions of machine learning and medical imaging, once again, medical imaging. And so with my colleague from Copenhagen, Veronica Chapiniga, we looked at the difference, again, between the two leaderboards. So there's two test sets, one that is visible during the competition and one that is visible at the end. So those are two test sets. People don't have the target to predict. And so what we're plotting here in blue is the spread for each algorithm of the difference between its performance on test set 1 and test set 2. So private leaderboard and public leaderboard. Okay? So the difference between the two is, as far as I'm concerned, evaluation noise. I give it two test sets that perform differently. Sure, all this is the statistical sample, more data, I get differences. And so what we see, and the paper I'm quoting here has more of these, what we see is that across several competitions, we have quite a variance, and the question then is, what should we compare this variance to? And so the red line is the difference between the algorithm that performed best, the one that won money, and one that's 10% further in terms of ranking of the algorithms. Okay, so maybe percent is a wrong term, but it's if you take all the algorithms, you rank them, and you take the one that's 1/10 of the ranks further. Okay, so that's the gap between the leader and one that was quite further away. And so now if we compare the gap, and sometimes I call this the winner gap. So if we compare this winner gap to the evaluation noise, and we look across the different challenges, in many challenges, this winner gap is actually smaller than the evaluation noise. Which means, if suddenly we were to sample new test data, the winners would be completely different. I call this diminishing returns, right? There's not really a win that probably carries over to new data. Sometimes sometimes the winner actually performs much worse on one data set than the other. Much worse on the private leaderboard than the public leaderboard. In this case, we have an overfit. And sometimes we have a natural improvement. So, but the most frequent situation is diminishing returns. Basically, people have worked their ass off on the Gaël competition, they've won, but probably random. Okay, we keep going. So I used to do medical imaging. This is why I'm taking many examples in medical imaging. Keep going, and we did an analysis of somewhat of a canonical problem in medical imaging, which is Alzheimer's disease diagnosis. That's important, could be useful. So we looked at the reported accuracy as a function of time. And you see different curves because there are different variants of prediction problems. You might try to predict Alzheimer's disease versus healthy control. That's not a very useful prediction because you're comparing basically symptomatic people to asymptomatic people. You might try to predict MCI, which stands for mild cognitive impairment versus healthy control. So once again, you're comparing symptomatic versus asymptomatic, the symptomatic whom we believe are healthy. And the most interesting prediction is probably either the green or the black line, which are across symptomatics, trying to distinguish symptomatics. Anyhow, the point being, there's not really an improvement in prediction accuracy over time. And if you look at the prediction accuracy as a function of the number of subjects in the study, it actually tends to go down. And that's something we found more than once, is that when studies are performed over larger data sets, the study doesn't seem to work as well. There are several explanations to this. One is that larger data sets are of poorer quality. And I often see this as a justification. I hear this as a justification that it's fine, we shouldn't worry about. But those poorer quality data are closer to real life. If we only work on high quality data, we're only working in our comfort zone. Okay, so my hunch is that, I'm sorry to say this, is that there hasn't been much progress on this canonical problem over the last 10 years. Slightly negative, pessimistic take, I'm sorry. And to go further, by the way, this paper, when we put the preprint, it was called How I Failed Medical Imaging. The final paper is called slightly better. But we tried basically to think about what were the bottlenecks. And if we go further, here we're looking at performance numbers. But if you go out, you go in the hospitals, you talk to people, there's much more than those performance numbers. Often the predictions that are published are done using data that is not reflective of a meaningful application. For instance, people have been looking at predicting malign versus non-malign carcinomas. So, you have a black dot on your skin. Is that a skin cancer? Yes, no. And it's a useful prediction problem. And so the goal is to be able to have mobile phones that take a picture and tell you, well, this might be malign, so you might want to have this checked. And people have shown that in some of the published studies that report a good prediction accuracy, the training base that they used had malign carcinomas that were circled because, hey, they were malign, so they needed to be removed. What did the algorithm do? Just pick up the circles. Now, people are laughing, but this happens much more often than you think. Sometimes in a very subtle way. Very, very subtle way. So even a good performance number may not reflect a useful application. There are all kinds of biases in the data. Now, I don't love the term bias, because bias is the loaded meaning, it is like something that has no bias. Nothing has no bias. But basically, the data is not useful in a real-life application. So quite often, even when we publish good numbers, the numbers don't bring any value to the clinic. Now, to move away from medical applications, because I don't want to be seen as bashing all medical applications, let's look at another thing. So a few years ago, we tried to look at tabular data. So I could define tabular data, but they're basically tables of numbers. And those tables of numbers don't have a very strong structure. Maybe the strongest structure that they have is that if you look at typical applications, each column, well, I said table of numbers, but technically they would be tables not only of numbers. You could have names, addresses, and everything, but we're kind of focusing on numbers here. And maybe the one structure that I can see if I look at applications is that the different columns have different meanings. I might have age, weight, size. So we call this tabular data. Many people call this tabular data. And over the last few years, so this kind of data is very common. If you look at any institution in the organization, it's typically the most common type of data. This is where kind of the internal data of the organization goes. It's your database everywhere. If you're looking at health, which is what I'm interested in, every hospital has tables and tables and tables of these things. So people have started getting interested in this, which I think is really cool. And there has been, more and more, increasingly, publications that show that if you devise specific deep learning architecture for this data, you can have really nice performances. And those are serious publications in good venues by famous labs. And so a few years ago, with a student, they were Einstein, we decided, well, this is an important topic. We're going to work on this. And so we started working on this, and we felt really stupid because we couldn't really get anything to work. I mean, things worked, but just standard scikit-learn worked as well, or sometimes better. And so we felt stupid, but after a while, we were like, right, let's be systematic. Let's measure things. Let's try to make things a bit objective. And we ended up publishing a paper, which was just a benchmark paper that compared things. This was not our goal. And I'm happy to say that this year we're publishing a paper that outperforms the benchmark. But a few years ago, our conclusion was, if you compare tree-based models to fancy things that have been developed, tree-based models outperform. And now if you account for things like time it takes to fit the model, they outperform both ways. You know, they're faster and they perform better in terms of prediction. Now maybe one difference, one of the reasons why we found this and people found something else, is that we accounted for hyperparameter setting. There's always a set of hyperparameters where algorithm B outperforms algorithm A. The question from a practical use case is rather, give me a budget of time to find hyperparameters, or give me defaults, or something like this. What's the average performance or average comparison of performance across data sets? Now, across data sets is a difficult problem because different data sets may have different characteristics. But in my opinion, an algorithm that is best performer on a single data set has little value in practice. It needs to be useful on a domain of data sets. Okay, so here we learned that kind of, things that were done 10 years ago tend to outperform things that are done today. So, this was kind of a slightly negative introduction about why we need more valid benchmarks. And those more valid benchmarks needs to capture the application setting. I kind of discussed this with the problems of how do things carry over to the clinic, and the generalization error. In machine learning, this is what we want, and I'll formalize this, we want the generalization. So, one of the things I think are important in terms of research is how do we make better benchmarks? And I'll be talking about this in this talk. I'll be talking about how do we think about our metrics, and how do we quantify generalization error. And then I'll zoom out and give a broader picture. Okay, so how do we do more meaningful classification metrics? And here the challenge really is that I'm going to come up with a number, and so that's the name of the game, right? We're comparing algorithms on numbers. Now, that's not the whole story, but it's still useful to have a number and to think about it. And now the question is, what does this number mean? Does it reflect something that I may find in an application? So with many people, a few years ago, we did a consensus paper on which metrics are useful for image analysis. Now that's a paper that's way too long, to be honest. We tried to make it didactic, and this was led by people from Linda Meyer-Hound's group in Heidelberg. And they did a remarkable work in making this didactic, but it's a bit of a big paper. I'm not going to walk into this paper because it would be too long. I will focus on this simple problem, classification. Okay? And I'll walk you through some thoughts about classification. And first, I'll take the problem of imbalance setting. So what if I have one class, let's even take a two-class problem. What if I have one class that's much, much more frequent than another class? It's a fairly common problem. And typically, by the way, in health, I'm interested in health. In health, most diseases have a low prevalence. Most diseases are infrequent in the general population. So you are in such a sector. Okay. So the typical metric that everybody uses, I do too, is the accuracy. So you count the number of errors. It's not very informative under class imbalance. If I had 90% of class 0, predicting only class 0 will give me an accuracy of 90%, right? Even though my algorithm is absolutely useless. So typically what is useful is to think about the confusion matrix. So the number of true positives, true negatives, false negatives that I have. And then it's interesting to distinguish the errors in class 0 and class 1. So We can talk about sensitivity, also called recall, which is the fraction of class 1 that's retrieved. So definition is true positive divided by true positive plus false negatives. Specificity is the fraction of class 0 that is actually classified as 0. So those are two values often used. And then we can say, well, I don't want to focus on class 0 or class 1. You don't want to focus on class 0 or class 1 because you can always, maximize one value but at the cost of not controlling the other value, right? You can always privilege class 0 or class 1 for the threshold really high or the threshold really low. So people use something that's called balanced accuracy, the mean between the two. What does this mean? How does this translate into an application? Now, I want to stress that, and people don't often think about this, that the sensitivity can be seen as the probability of predicting a positive class given a true positive. Okay? Probability of predicted positive given true positive. Sensitivity is probability of predicted negative given a true negative. It's useful to think in these terms. But are we asking the right question? Are we interested in the probability of the prediction given the truth? Not in the application setting. In the application setting, we're interested in the probability of the truth given the prediction. So that's 101 probability. I can go from one to the other using Bayes' theorem, so I can relate the probability of the truth given the prediction to the two other probabilities, and I have, so you write this down and there's the prevalence that comes up. Okay? So I've written the formula here. So this, by the way, probability of the truth given the prediction is the positive predicted value, and there is the converse probability of true negative given predicted negative is the negative predicted value. In medicine, by the way, this is what they use, and for many years, for a decade, for instance, I wondered, why are they using these strange metrics that we don't use in machine learning? Well, the reason is that these strange metrics give something that is meaningful for the application. And so then you can create a summary metric that's, basically the average of the PPD and the NP. Now, one of the reasons why we don't like this is it depends on the prevalence. You can't compare PPD and PD markedness on data sets that have a different prevalence. So it doesn't characterize only the predictor, the classifier, but also the data set. And we don't like that. But in practice, by the way, it's the value of the predictor probably depends on the value of on the prevalence, or rather on the target population. Now you can go a bit further, and this, by the way, is well known to biostats. So we just found it again, reading old biostats books. And you can use odds. Biostats uses odds a lot. These odds were odd to them. The definition of the odd of an event is the probability of the event divided by the probability of not the event. So P of A divided by 1 minus P of A. And then you can do odds ratio. And there's one thing about odds ratio is that odds ratio compensates things. Things cancel out. And so a simple algebra will tell you that if you take the odds of true positive given a predicted positive divided by the odd of a true positive, you do the math, it's really simple, and it's done in the appendices of the paper so I think here's the book chapter technically. Then you find something that is independent of the prevalence. Basically the prevalence cancels out. This is known as the likelihood ratio of the positive class, and you can do the same thing for the negative class. This is a useful metric because it does characterize the gain of information that your classifier brings. Because it gives you the odds, it gives you what's known as the post-test odds divided by the pretest box, where the classifier here is seen as a test. Just like a COVID test, for instance. It's the same usage. I have a black box, I give it an individual, and it gives me a value. And it's not dependent on class preference. So this is not a very popular metric, but it could be a useful metric to inform the usefulness of a classifier given class and balance. And once again, it's independent of class preference, so I can, for instance, measure this metric on a balanced data set, such as a case control study, where I've artificially oversampled, artificially, for instance, downsampled the control population and oversampled the disease population, and then, which is like your typical data set that we use when we do the medical prediction from medical images, and then extrapolate to the value on the general population. Does that make sense? Okay? So beyond the specific, I don't want to like sell the LR plus or LR minus. What I really want to, the point I really want to make here is that we need to think about what numbers mean and how they can be used. And I'm absolutely convinced that we need to think in terms of probability of the truth given the prediction and not the converse. Okay. To move on and give you another example of how we can think of things, I want to discuss confidence scores and calibration. So the reason why I want to discuss this is because in any medical application, the first thing a doctor will ask you is how confident are you about this prediction? The reason they ask this question is that they're actually making a decision, multiple decisions, and they need to factor in all kinds of different things. The patient's preference, the family's preference, the availability of material in the clinic. And in general, by the way, even if we move beyond medicine or beyond a human being making a decision, in general, we give prediction scores, but in practice, those prediction scores are going to be turned into decisions, and those decisions maximize the utility function, and either we write down the utility function that they maximize and we do the math, it's somewhat tedious, or we need to express confidence score because the downstream decision engine, whether it's a human being or operational research code, will use confidence to maximize expected returns. Okay, so the question then is, can we interpret a classifier score as a probability? So your classifier gives you a number. It's the distance to the hyperplane. It's the unthresholded output of a softmax. Can I think of this as a probability? And the narrative in machine learning has vastly focused on something that's called calibration. The definition of calibration is a classifier is said to be calibrated if its average error rate for all samples with score S, output score S, is S. If I take all the samples for which my predictor has given the score S, I average the error rate. If I find S, I'm calibrating. Typically, the way it's done, and there are better ways to do this, is it's computed on bins taken on the scores. And so people look at the expected calibration error, the ECE, and it's the average error, and you can take an L1 or an L2 on the bins of score. And so then people look at calibration plots, and it tells you whether, they plot the observed fraction of positive as a function of the mean confidence score, and if I'm above the curve, my classifier is giving a mean confidence score that is systematically above the observed fraction of positive, so it's overconfidence, and if I'm below, it's underconfidence. And this is really where the discussion is today. I want to stress that this is an average error. Average over the bins. And it doesn't really control that my confidence scores really correspond to the probability that I may be interested in. So, a calibrated classifier can assign a score of 0.6 to individuals, but in all those individuals I may have two subgroups. On one of them, it may be accurate to 100%, and another one, subgroup, it may be accurate to 20%. So my classifier is calibrated, but in no way does it control individual probabilities. So to make decisions, it's severely suboptimal, at least at the individual level. Maybe at the microscopic level, it's optimal. So for what we call medico-economic questions, it's relevant, and maybe not, that depends on the setting, but for the individual, it's terribly unfair. So, calibration in no way controls individual probabilities. And in the literature is just rife of confusion, where people tell you the classifier is calibrated, and yep, they go on, and the reason is the classifier controls the individual probability. The classifier has estimated P of Y given X. It's all over the place, all over. Okay, so how do we control P of Y given X? There is a family of mathematical functions that are called proper scoring rules that create distance-like objects where you can give them the observed labels, and the observed labels are binary. Never did I observe the probability of someone to become sick. I observed discrete individuals. You know, one individual becomes sick, one individual doesn't. So my Y is discrete, and my confidence score is continuous. And a proper scoring rule on expectation is minimum when the candidate's score is equal to the distribution that generates the discrete Y's. Okay? So the nice property of the proper scoring rule is that even though I've never observed the probability distribution, it's minimum when I actually have the probability distribution. One example of proper scoring rule is called the Brier score. It's just a fancy name for just saying, you know, the squared error. Another example of proper scoring rule is the models. A loss that is not proper is the hinge loss. People don't use the hinge loss anymore, but back when we were doing SVMs, we were using hinge losses, and hinge losses are not proper. It's easy to see because the hinge loss is zero on a lot of the space, and clearly it's not controlling errors here. Okay, so people don't use Brier scores, don't use proper scoring rules to report performance, or very seldom. I'm not exactly sure why, but one reason may be that they cannot be interpreted as error rates, and people like to interpret things as error rates. Another reason is that there is no clear scale. You know, if I give you a Brier score of 0.5, you don't know if it's good or bad. I'll tell you why. Okay, so we can go in a bit of theory, we can zoom out, and we can look at how to decompose those scoring rules into error rates. And this is, by the way, this is all literature that we have recently contributed to. And so if you take a proper scoring rule, you can decompose it in a sum of different terms. And the first thing you can do is that you can split out what I'll call the irreducible error. The irreducible error is the error, the remaining term of your proper scoring rule, even if you have the perfect probabilistic prediction. So if your prediction is probabilistic, if you don't have enough information to conclude deterministically on the label, then your irreducible error will be non-zero. And then the remainder, which is sometimes called the epistemic error, can be also split into the calibration errors. So the calibration error is what we just saw before, and the remainder, which is the grouping, or the grouping error. Okay, so calibration can be seen as an error on the average. You know, on average, across all individuals, my prediction is off. My probabilistic prediction is a certain amount. So it's an average error, and the grouping error can be seen as the remaining term, which is basically a form of generalized variance. So in a sense, what we have here is a mean variance decomposition of the error. It's slightly more fancy than this because you need to play a bit with proper scoring rules, but it's really the idea. So this was known. I think it's Gaël who contributed this maybe 15 years ago. But this was feared because I got this decomposition, but I don't know the irreducible error. I can measure the calibration error, but I can't measure the rest. So what what we did recently, but I'll explain this on the next slide, is that we looked at the grouping loss and we looked at how to characterize it. So if I had access to the true probabilities, I could plot things like this. This is some form of calibration plot, but I'm plotting the true probabilities. And what you can see here is that my classifier is calibrated in the sense that its errors lie on the diagonal, but there is variance. The true probabilities don't always correspond to the confidence. Okay? So in a sense, this is what the grouping loss is measuring. It's measuring the spread here. So it's characterizing the fact that the classifier is overconfident on some samples and underconfident on others. But I can't plot something like this because we need the true probability that I don't have access to. And one thing I can do is do what's known as test retest. So I can apply the classifier multiple times to it's not apply the classifier multiple times to the same individuals. It's randomly draw multiple times the same individuals, which is not always possible. I can't follow the life of the same person twice. If I run experiments in a reproducible way, it may be possible, but it's seldom possible. So what we did last year with Alexandre Pérez-Debel and Marine Le Morvan is to contribute an estimator of the grouping. And the way it goes, and I will not go into the mathematical details, the way it goes is that we estimate true probabilities on well-chosen bins. So we're going to divide the space in bins that are data dependent. And on each bin, we estimate the true probabilities. And given this, we can estimate this variance. Now, there's much more to it. The ingredients first, technically, this is not an estimator of the grouping loss. This is an estimator of the lower bound of the grouping loss. Second, when you're estimating probabilities of discrete elements on bins, and the bin starts to get really small, and you have few elements, you have systematic biases in your estimations. In the paper, we characterize these theoretically, and we compensate for them. And this is why we get a fairly tight lower bound, because then we can optimize the bins to be really small. Our bins in practice, we found that we can have bins with only a few elements in them. They compensate for biases due to the small numbers. Okay? And because we have really small bins, and because they're optimized, we use decision trees to optimize them. Because they're optimized on the data, and basically they capture well the heterogeneity of the prediction, we get a really tight lower band. Talking slowly. Okay, so in practice, the big is that this gives a good estimator of the grouping loss. It validates this on simulation and applies this on real data. Okay, so I just give you a small example of things we can think about in terms of classification metrics. The first thing I want to stress is that machine learning, image processing, probably the same metrics. It's good and bad. I mean, we also need to compare the things, but we need to think about those metrics really well. And I'll give you some direction to think about these things. You know, thinking of in terms of probability of the truth given the prediction and not the converse. And thinking in terms of uncertainty, which I think is really important. But the important thing, you know, is zooming out. A single number never tells the whole story. Or maybe you have an expected utility in dollars, and that's your single number. But we seldom have this because we're seldom connected enough to an application. I said dollars, it could be expectancy or things like this. Okay? If I understood well, we have a fair amount of time, don't we? Okay. Are there any questions? No? Are you falling asleep? Okay, so I want to talk about another thing now. I want to talk about the variance. So, the reason I talk about this variance is if you go back, I started the presentation by showing you horror stories of evaluation gone wrong. There were two aspects to those horror stories. The one that was most obvious is probably related to variance. You know, people would try things out, they see they worked, but the evaluation was noisy. The other aspect of the horror story was it didn't carry out on the application. That's harder to see. So here, I just want to think about how do we quantify a bit this error that we have in our estimation procedure, and how do we do estimation model evaluation in machine learning? Well, for good reasons, we split the data in a train set and a test set. And before I go into details, we first need to stop a bit and think about what's the question we're asking. And I want to stress that there's two different questions that are relevant. One of them is we're benchmarking a prediction rule. So we're given a predictor, f that goes from x to y, and this is what we try to benchmark. And the second scenario is we're benchmarking a training procedure. We're given a procedure that, given training data, outputs a prediction rule, a hat, that goes from x to y. Those are two different scenarios. For instance, if I'm a medical doctor and I want to quantify the reliability of the tool that I'll use to diagnose people, I'm in scenario one. If I'm a computer science researcher and I want to publish that method B is better than method A, I'm in scenario two. One of the difficulties is that people mix up the two scenarios, and I'll show you that they shouldn't give rise to the same evaluation procedure. Okay, let's first look at scenario one. Benchmarking a prediction rule. There are many things to keep in mind. One of the things to keep in mind that we seldom discuss in computer science is the notion of external validation. I need my test data to be different enough from the trained data. One of the reasons is that I need an independence assumption between the trained and the test set. Elsewhere, it's not valid. So we shouldn't have things like repeated acquisition of the same individual in train and test, because that means I'm not measuring in any way how do I carry over to other individuals. And what I found working in medicine is that biostatisticians would really like us to show generalization to new sites or later in time, things like this. One of the reasons behind this, and I'm not going to go into details, is that this kind of convinces us that the black box predictor hasn't learned something trivial about the data that will not generalize. We don't do this, and the reason we don't do this is that all our learning theory, well, most of it, is for IID data. And that's fine. We do the theory, we can't do it. And it's fine. It's just that we should, I'm convinced these days that we should put a kind of a stronger test on our algorithms, elsewhere they're not useful. And then, once again, it may be trivial, but our test data must be representative of the target population. If it's not, we're coming up with numbers. Those numbers are not useful. And so there are many ways to do this. We can match statistical moments. We can optimize the test data to minimize the confounding association. That might be important. It's just we need to think about this. Once we've done this, I want to point out a fairly trivial problem, but that's quite important, is that we have sampling noise in the test set. The test set is just, a small number or big number of test examples, and it's just a drawing from the general distribution. And so, if I were to draw different data, I would get a different number. And if I'm looking at the simplest metric that I can look at, the accuracy, and I told you before that maybe I shouldn't be looking at the accuracy, but at least I can easily do the math. If I'm looking at the accuracy, and if I'm modeling the accuracy as a binomial, as a coin flip, accuracy of the classifier is a coin flip, so this gives me the distribution for the accuracy of a test set being a binomial law. It's really, really simple math. And I like simple math because then I can reason about them. So what I've plotted here is the binomial law on a test set of 1,000 data points. And the error bar that I've given you is the error bar at the low T 5% confidence intervals. What I want to stress is that it's bloody large. And this is 1,000 test points. Many applications have less than 1,000 test points. The errors go down as square root of n. So they go down slowly. And to me, this is exactly what we're seeing here, right? If I'm given a finite test set, it has evaluation error. And there's nothing I can do about it. I'm basically limited by my test set. In machine learning, we often worry about the limit that we have by our train set. We want more training data to learn a better model. We have the same problem in the test set. And it's brutal. Okay, so as I said, it goes down at square root of n. So I've done something really stupid here. I've given you a table of the binomial confidence intervals as a function of the unknown average accuracy and the size of the test set. I stress this is the size of the test set. This is not the size of the full data set. And I just want to stress it goes down really, really slowly. So I think this is really important to keep in mind. I keep this in mind when I review papers. It's also important to keep in mind to know when to stop. If you're basically getting improvements that are on the order of magnitude of your confidence intervals on your test set, you don't know what you're doing. It's time to stop. And back to the competition on autism, some people should have stopped earlier. I always think this is really important to keep in mind. And this is why in the book chapter we just gave this table. You can come back to it. It's also very easy to compute on. Okay. So the first part is fairly easy because basically what I really have to worry about is the sampling noise on my test set. And this is a very simple model. In practice, my test set may be correlated, it may have heterogeneity, things like this, but the error is probably actually going to be wider and not narrower than this. So this is kind of a conservative table. Now if I want to benchmark a learning procedure, which is maybe what I'm interested in as a computer scientist, it gets more complicated. And the reason it gets more complicated is that there are many arbitrary components in my learning procedure. And so David Picard has this really fun paper where he plays around with a random seed and just claims that, well, he can pick a random seed. That means that he gets really, really good results on, I think, image net. I don't remember which image classification algorithm. And I've had actually very serious discussion with people who are like, I can tune the random seed and it works better. I can show you it works better. What's wrong with this? Well, if I'm in scenario 1, and so by the way, the argument was, well, I'm avoiding to fall into bad local minima. If some models have terribly poor local minima. So by tuning the random seed, I'm checking that I'm not falling into bad local minima. To be honest, this is a relevant line of thought for scenario 1. Because scenario 1, I tune the random seed, I avoid a bad local minima, I give you the model, you can use it. I've avoided the bad local minima. However, it's incorrect for scenario 2, because a random seed will not carry over to new training data. So once again, this really shows us the importance of separating the two scenarios. And it's true for random seeds, but it's true for all kinds of different things, right? I mean, random seed may be in the way in it, and maybe in the dropout, in the data augmentation. So when we're comparing learning procedures, we need to control for all these. And so when I was at MILA a few years ago, we did a fairly extensive study, very compute intensive, where we looked at the different sources of variance in a machine learning benchmark, looking at a bunch of different applications, but some of them in language, in image, on modern neural networks. And so the way we did this, by the way, is we reran evaluation many times. It was extremely costly. And I want to stress that, you know, all these factors are important, and we can modify all these things, and they all lead to modifying the end value that we look at. But the most important one was the split between the train and the test set. If we review the split between the train and test set, we get a much bigger variance in our benchmarking number than if we look at, for instance, the randomness of the weightings. So what is this telling us? It's telling us we should probably benchmark our algorithms across multiple training test sets. Which, by the way, is something we used to do 15 years ago. It was called cross-validation, and we stopped doing because our algorithms are too computationally expensive. I personally claim this is bullshit, because I personally claim that if we're going to use very computationally expensive algorithms, so expensive we can't benchmark them, we're doing things wrong. I'll come back to this. Okay, so I argue we need to reintroduce cross-validation. One last thing, hyperparameters. So many people, myself included, are convinced that a lot of applications come with suboptimal hyperparameters on some models, but not others, and hence come with invalid conclusions. So we're convinced that hyperparameter selection should be part of the evaluation. And here, one way of doing it, I'm not going to claim that's the optimal way of doing it, is to use random search. Random search is you basically stipulate distributions on your hyperparameters and you draw values of the hyperparameters. So it's basically a random exploration of the hyperparameter space. It has the benefit that if I stipulate a non-important hyperparameter, here is hyperparameter 2, the one that's vertical, and I keep sampling it because the sampling across hyperparameter 1 and hyperparameter 2 is incoherent, is independent. My budget that I'm spending for hyperparameter 2 is useful for hyperparameter 1, which is the important one. So this is one reason why typically random search is to be preferred to grid search when you get more than 2 hyperparameters. For 2, it's probably not the case. Okay? Now, the benefit of random search is that also if you want to evaluate noise created by suboptimal hyperparameter selection. You may be able to do this because you may be able to, for your 10 or 5 best results from random search to spread across those 5 best results. Now, if you think about this, I'm hiding a few problems. There's no mathematical rigor in what I said. But at least in terms of ballpark estimation, you get something. This is, by the way, how we did those plots. The variance that you see here is variance that is that we see when we subsample random search. Okay, so how can we have a benchmark that a benchmark training procedure and somewhat controls arbitrary fluctuations? I call arbitrary fluctuations fluctuations that will not generalize. Well, it's quite easy actually. Sample everything. Sample the data sampling, do multiple random data splits. Sample all the arbitrary choices. The seeds, data augmentation, and everything. Those are arbitrary. You just sample them. And do a hyperparameter optimization also by sampling. And just take the best ones. Okay? And if you do this, and technically the difficult part is the hyperparameter optimization, and the paper with Xavier Boutillier discusses more in detail. If you do this, you get an idea of the arbitrary variance that you're not controlling in your benchmark. And to be honest, doing this in a mathematically rigorous way is very hard. I don't know how to do it. But sometimes doing it approximately right is better than not doing it. We need an estimate of how things vary. Okay, I don't want to get too much into details, but I want to talk a bit about statistical testing. And I want to stress that statistical testing, the reason I want to talk about statistical testing is that we're going to do a benchmark. We're going to come up with numbers. Ideally, those numbers now come with an estimate of variability of the numbers. I have numbers and I have plus and minus, for instance. And we want to conclude. Yes, we outperform everybody because we want to publish. And the question is, how do we conclude? And one answer is statistical testing. So statistical testing is actually very difficult on those things because we don't have independent draws. If we are working across multiple folds, we're never working across new data. We're always drawing the same data from, we're doing training test splits and we're always drawing the same data. And that's a problem that's been known for quite a while. And people have tried to correct for it, but it's really hard. So, I don't want to get too much into details, but I want to stress that you shouldn't be doing like simple statistical tests that may seem reasonable, like a t-test or Wilcoxon test across faults. I've seen people do that. I may have done that. It's not that. One reason to see this, by the way, is that I just draw more folds and more folds and more folds and more folds. If I keep drawing more folds and more folds and more folds, I'm increasing my sample size. And so standard statistical testing, if you increase your sample size, at some point, it's going to be significant. Significance testing is a measure of sample size, in a sense. And so in the paper with Xavier Boutillier, we advocate for a different approach, which is to say, null hypothesis significance testing is not what's relevant. What's relevant is we want to have a gap between two algorithms. I want to be able to, try my algorithms on many different data splits and everything, and I want to see that one is above the other more than 50% of the time, and more than it needs to be not 50.0001. So we impose a gap. We say more than 60%. In the paper, we calibrate this gap, and the reason we calibrate this gap by looking at historical data. And I don't remember the number that we put. This can be linked to what's known as Lehman-Pearson testing. I don't want to go into details, but honestly, this boils down to a very simple rule. Well, you can boil this down to a very simple rule. Look at the variability of your algorithms when you sample many things. If the difference between two algorithms is bigger than the variability, you have a result. If it's not, you don't have a result. I just want to stress that it's something different than standard Fisher null hypothesis statistical testing, because standard Fisher null hypothesis statistical testing looks at the number of draws you've made, and if you've made many draws, you can have an arbitrary difference that is significant. Okay, just to summarize this part, if you want to look at uncertainty, it's important to distinguish two scenarios, whether you're benchmarking the learning procedure or benchmarking the learn predictor. The scenario, sorry, I clicked the number. The scenario where you're benchmarking the learning procedure needs to account for many sources of variance. It's important. And as I said, sample everything. Have statistical significance in mind, but don't overdo it. Or if you overdo it, do the math. Are you all tired, or do you want me to talk about something else? Okay, now I'll talk about something else, and maybe I'll give you a bit of a reason why I'm talking about this. About 6 months ago, I was asked to be in an important commission about AI, nominated by the president with many important people, and yada, yada, yada. And we did many interviews looking at many aspects of the problem. And this generated kind of new thought for me. And I'll expose some of those new thoughts and how they're related to benchmarking. And to go back to research or technology, the current narrative is that big neural networks are solving everything. And it's being shown by Alex Smith in computer vision. This is a quote from the Alex Smith paper. They believe that their results can be improved by simply waiting for faster GPUs and bigger datasets. And more recently, Richard Sutton published a blog post called The Bitter Lesson, where he basically said, it's just computation. It's all just computation. And so if we go back in time, in 2016, everybody, me included, was saying, in a few years we have autonomous driving. This was published, people were saying this. But in practice these days, experts don't believe it's really close. I've talked to experts of autonomous driving, and they don't think it's going to happen in the next few years. So we severely underestimated the difficulty, and maybe we severely overestimated the capacity of our systems. So, we looked at, with a few colleagues, we looked at the results on benchmarks as a function of size. Size is hard to measure, and that was the 50. So what you can see is that, well, unsurprisingly, it goes up and then down. There's no surprise here. The maximum size, when comparing the size of the model in gigabyte, because that's the only way we could compare things across application, the optimal size varies across problems. If we look, for instance, in computer vision, if I look at object detection, the optimal size is smaller than if I look at scene understanding, because scene understanding is probably a more open-ended problem. For natural language, it's somewhat similar. If I look at text embedding, it's smaller than if I look at benchmarks of artificial general intelligence that people do in large language models. So the first thing that we see is that, unsurprisingly, it's not always bigger is better. And on top of this, and here I don't have figures to point to, I want to stress something I've said many, many times. Those are just benchmarks. benchmarks don't carry over to the real applications. And that's something that's really, really hard to get machine learning researchers to understand. But you know, if you're looking at self-driving, for instance, you have your benchmark, but then you need to control for the unusual event that will happen and kill someone. That's not in the benchmark. Medical application gets the same thing. So this is a picture that's overly simplified compared to real application. Why am I pointing this out? If you look at the size, this is the training compute used as a function of time of highly visible, the well-cited models. This is a log plot. You can see that it's going up a lot. By up a lot, I mean faster than linear in a log plot. So this is a hyper-exponential scale. Something that's striking is that it's actually going faster than the size of the largest computer on Earth. And we caught up. I mean, we've gone from an insignificant fraction of the largest computer to something that actually uses many days of the largest computer on Earth. The cost, so people say, it's fine, hardware is getting better. Well, no. The cost is actually ballooned up. So hardware is getting better, but we're using more and more of it faster than it's getting better. We're looking at training costs. I mean, here, those are the numbers we have. But between us, people tell us that the training cost of a large language model is in the 10 to 100 millions because they don't get it right the first time. This is what we get when we audition people. 10 to 100 million. Okay, this is just research. How about production? In production, what's important is the inference cost. You know, how much is this going to cost me each time I use the model? Same thing. Inference cost is going higher than the efficiency of GPUs. So our models are less and less sustainable from an economical perspective once we put them in production. The costs just don't add up. So are we the baddies? Are we just, making overly complex models? And this is really the question I'd like to ask. This is important because scale benefits some actors rather than others. If you want a lot of individual data, who does it benefit? The social network. If you want a lot of compute, who does it benefit? The GPUs providers and the cloud providers. The people who are actually winning most in this race are, one, NVIDIA, two, the cloud providers. And I'm just, of course, part of it is, this is how it goes. It is true that larger models work better, but they're completely offsetting the power balance. And we need to think about how we play this game. And even if we're going to create a startup that's going to do whatever large language models to answer your mom on WhatsApp, will that startup be viable given the cost? Who's going to long-term benefit from this? Is that startup going to long-term benefit from this? Or is it going to crash in a few years because VC funding dries out and gets bought up by the big players? I'd like to say that what we have is 101 bubble. And what happens when a bubble crashes is that the big players buy out the small players. This happened, the dot-com bubble 20 years ago, it will happen again. That's cool, we can play the bubble. I mean, even myself these days, I have my own startup. But we should be aware of these things. And I'd like to say, we need to play strategic, and we need A, to be in the right place when the bubble bursts, but B, can we not play the bubble? Can we understand the trade-offs, and can we improve those trade-offs? This is what we should be doing. And looping back to model evaluation, we need to measure those trade-offs, and we're not measuring those trade-offs. So, I worry that we're basically building the SUVs of tech. And I personally hate SUVs, we'd like us to build the bicycles of tech. Okay, so there's nothing new here, right? Industries have always overestimated their value. pharma, crypto. There's really nothing new here. But as scientists, we must not play this bubble, and we must give out pictures that are well understood. This goes back to benchmark. Thank you.
Thanks a lot for your presentation. We will now be taking questions from the audience here, as well as on Zoom. If you have a question, you can write it in the chat, and I will read it, or unmute yourself.
Thank you for the nice talk. Out of all the new tools that you described, how well are they accepted? And even when you review, you come up with a different you need to convince people.
Yeah, so what you're asking is an important question. So you're basically saying we're in a social game, and if we don't master the social game. So there's two answers to this. One is we can do papers that we visit our norms. I end up doing these every few years. It's not by design, it's just like I get curious. But also I see the evolution. For instance, at Europe this year, Europe is crazy. There are 25,000 submissions. I'm scared. But at Europe this year, there's a benchmark and evaluation topic in the main conference. So it seems that research on those questions is becoming quite visible. Second, science is never about a number. That's something really important. Science is about a narrative. And in computer science, we tend not to accept this because we're very number focused, and we're somewhat came from math, but it's this. So it's about writing the paper, making the point. I often joke that I went into computers because I wasn't good with people. So we're not always very good at this, but we need to get better. And long term, those are the good papers. Those are the papers that get cited. So, if your community uses a metric that's a really bad one, you still need to report it, because then you'll get in trouble if you don't. But you can report another one, and you can try to make a convincing case about it. Thank you.
Question about something you said when you were talking about training procedure benchmarking. It was when you made the difference between grid search and random search. I thought you said that it was better to do random search, and I've not understood it. So if you could just.
Okay, so the question is a grid search versus random search. So the simple take-home message, by the way, is the rule we usually give people is if you have one or two hyperparameters, most likely it's better to do grid search. If you have more, most likely it's better to do random search. The reason being, if you look at this diagram, I've taken a situation where I have one hyperparameter that I must tune very finely, and another one which I must tune quite roughly. If I do a grid search, I haven't drawn the grid search in this figure, sorry. If I do a grid search, the budget I'll be using for hyperparameter 2 will fall in the line of constant hyperparameter 1. So all this budget is of absolutely no use to hyperparameter 1. And if you take the extreme case, hyperparameter 2 was actually not useful to tune at all. I'm wasting my money. If I do random search, I have incoherent sampling in compressive sensing, signal processing, but I have incoherent sampling. And so it's still useful for hyperparameter 1. And so this is what we're showing here, And it's empirical study hints that typically when you have more than two, not two, but more than two, you're into this scenario. The difficulty, of course, is specifying the search. It's the grid or it's the sampling. If you know your optimal, you don't even need to specify the search. You can directly specify the optimal. And so I like to think of grid search as also a random process in the sense that the grid is not absolute. The grid was chosen by someone, even if it was chosen by the live data. It was chosen by someone. You could have chosen a different grid, and you'd have a different. Thank you.
Thank you very much. I found that in the end very interesting your philosophical points about SUVs and I'm with you because I think the only region that can do this SUV kind of research is America, right? Because they have big money and it doesn't matter if it costs 10 billion or 100 billion. Yeah, they can make it happen. So I mean, what should Europe do? And I think strangely there's some analogy with China. Because, I mean, in China, they have all these import restrictions. So basically, they can't even use the best GPUs, right? So how do they, but they have great results in machine learning. How do they do it? So I think they do it smarter, right? So this one example is, so I had a talk 2 days ago, and I talk a lot about generative models, like videos and images and so on. And for example, there now, there is TensorRT, which is NVIDIA's acceleration framework, and then the Chinese made one, which is 10 times faster than TensorRT. How can they do it, right? So it's very interesting. But so I feel Europe probably the way they must make such a way that it's more based in mathematics and more in better algorithms, rather than putting 10 times as much compute. I don't know. What do you think?
There are many factors to it. The first thing is, I don't think this is a technical problem. I think this is 100% a social problem. And with regard to GPUs, well, there are different aspects to it, right? There are many aspects to it. One is, where are we headed? Right? I think we're headed in trouble, but there's nothing new here. The usage of coal, charbon, has been going up over time, ever since the Industrial Revolution. Today is the day we're using most coal in the history of humanity. So it's just, it's super classic. This is why I quote the SUV. Right? The SUV is a social thing. People have SUVs because they have weak egos. And people do have weak egos. Same thing for neural networks. So, now that's one problem. I worry, where are we headed? We're not headed in good directions. But there's another problem, that's more like an ecological problem. There's another problem, which is a problem of geopolitics and power balance. Here, from an economical perspective, we need to be careful. We are buying compute from the US. We are buying GPUs. We're renting. So we're buying physical GPUs. We're renting GPUs in clouds. We need to be strategic. And here, the report of the Commission advocates for fostering data centers in Europe because it's cheaper long term to buy the GPUs and have them and use them, if we're not stupid about which GPUs we buy, than to rent them. In terms of economic balance, it's better. We also advocate for investing in GPU design. That's more of a gamble. But if we don't, I don't see where we're headed. And then, the question is, and I don't have a single answer to this, the question is, how is going to be the power and the value distributed? That's what I worry a lot about. And there are two answers to this. One is we need to take collective decisions on this, but I've become convinced over the last 6 months of playing at government level that it's not all about regulation. You just can't regulate people's behavior, and regulation is also going to benefit certain actors rather than others, and regulation is like sausages. You don't want to know how it's made. I can tell you. It's basically power games, and you get into something that's well documented. It's called regulatory capture. And this is what's coming. So there's this social work to be done, and I think it needs to be done. And I don't have a simple answer to this. An answer that I have is that we are actors of the system. We're actors of tech. So we can choose the problems we work on. We can choose what we facilitate. This is something that, as computer scientists, we can do, and this is what I would like to do personally. That's not a very good answer, by the way. That's all I have.
I find it interesting because in China now, basically they developed CUDA-compatible GPUs by themselves, which I think is quite an astonishing achievement, but then they're not really fast because they don't have the fabrication, right? And now it's about, yesterday I talked with the NVIDIA guy, and they were saying they expect that China will invade Taiwan in order to get their hands on the fabrication of our good GPUs. So it's so interesting, I think, that there's this kind of war in the air, part of because of deep learning. I think it's a factor for that.
I don't know if a reason to invade China.
Well, there are many reasons, but I think one contributing factor is this, because they don't have enough compute. I mean, China has the craziest data, like no privacy, everybody using WeChat, the government gets all the WeChat data. No country has such a data. But
I think it's really a very naive thinking to think that if China invades Taiwan, they get the founders, the chip factories, because those chip factories they use tooling that's from AMSL, which is a Dutch company. So something that so for geopolitics of chips, most chips are made in Southeast Asia, most in Taiwan, Taiwan TSMC, Taiwan but a lot subsumed. Investments are in the factory is in the hundreds billion euros. To give an order of magnitude, the budget of the French state yearly is a bit above 1,000 billion euros. So we're looking at a sizable fraction of the budget of the whole French state to build a new chip factory. But the core component of those chip factory is hard UV lithography that is designed in North Belgium, South Netherlands. So it's an interlocked economy. You're right to point to the fact that hiding behind strategic decisions here are geopolitics, which are related to economy, so value, who sells what, but control. Where does the data go? And going back to the fact that we can't regulate our way out, if we don't build the hardware, if we don't build or if we don't operate the software, if we don't have Google, Microsoft, we can't regulate. We can try, we can go all the way. Yeah, well, nothing's going to happen because we're not a player in this. But we are in Europe.
I believe you have to go now.
I do have a meeting now. Sorry for taking all your time.
So thanks a lot for coming.